Mathematical induction. What is mathematical induction? It's a method of proof, of mathematical proof, that's used to prove that something, a formula or a theorem, is true for all positive integers. This will make a little more sense as we go through and actually use it. Let's start by considering the regions of a circle. Consider a circle with a certain number of points on it. Let's start off with 2 points. We want to know how many regions will be formed, how many regions will the circle be divided into if each pair of points is connected with a chord. If we have 2 points, we get 2 regions. We have 3 points, we connect them all, we get 4 regions. If we have 4 points and connect them all, we have 1, 2, 3, 4, 5, 6, 7, 8. And we have a pattern here. We have 8 regions. We have powers of 2. This is 2 to the 1. This is 2 squared. This is 2 to the 3rd. We have 5 points. 1, 2, 3, 4, 5 points, and connect them all and around. And it's a little bit difficult to see. If you do it neater on yourself, you can see that with 5 points we get 16 regions, which is 2 to the 4th. At this point, we've seen a pattern, and we could make a conjecture that with 6 points we would have 2 to the 5th, or 32 points, 32 regions. We have not proved it. It's a conjecture. So if we find the number of regions with 6 points, will it prove the conjecture? No, because if there are 32 regions, all you have done is show another example to support your conjecture. If there are not 32 regions, you've proved the conjecture wrong. And in fact, if you go ahead and try the circle with 6 points on it, you will find that there are not 32 regions. Go ahead and try it. There are 2 important things to remember. Number 1, you can never prove a conjecture is true by example. And number 2, you can prove a conjecture is false by counterexample. We're going to be using the principle of mathematical induction to prove a conjecture is true. Basically, what we need to do to prove a conjecture is to show that something works the first time, assume that it works this time in any given time, prove that it works next time, and then draw the conclusion that it works for all integers. In mathematical terms, what it means is we show that it's true for n equals 1. We assume that it's true for n equals k. Then we show it's true for n equals k plus 1. And then we can draw the conclusion that it works for all n greater than or equal to 1. The key word in step 2 is assume. We're not trying to prove that it's true for n equals k. We are assuming that it is true, and then show that it's true for the next number, n equals k plus 1. If it later turns out that we have a contradiction, then the initial assumption was wrong. Let's see how this works. We want to prove that 1 plus 2 plus 3 plus ... plus n is equal to 1/2 n times n plus 1. So step 1 is to show that it works for the first term. The first term is 1. So 1, we hope, is equal to 1/2 of n is 1 in this case, times n again plus 1. This is 1/2 times 1 times 2, which is 1/2 times 2, which is 1. So it does work for the first term. Step 2 is to assume that it works for n equals k. That is that we assume that 1 plus 2 plus 3 and on and on and on plus k is equal to 1/2 k times k plus 1. We're assuming that that's true. Step 3, we will try to prove it for the next number, k plus 1. To do this, we want to add k plus 1 to both sides of the equation. So we have 1 plus 2 plus 3 plus k plus k plus 1 is equal to 1/2 k plus 1 plus k plus 1. We're adding k plus 1 but to both sides of the equation. Next, we want to write out our goal. We want to give ourselves something to aim for. We started out assuming that 1/2 k times k plus 1 was the sum for n equals k. So when we go with k plus 1, we're going to replace every k with k plus 1. So we get 1/2 k plus 1 times k plus 1 plus 1. That's the same sum with k plus 1 substituted in for the k. So now we go back to the sum where we had 1/2 k times k plus 1 plus k plus 1. Remember when we added k plus 1 to both sides? And what we want to do is manipulate it so it looks like that goal. So the first thing we'll do is we'll factor out the k plus 1. So we'll have k plus 1 times 1/2 k plus, when we factor out the k plus 1 here, we're left with 1. Now if I factor out the 1/2, I'll take that out. I'll have 1/2 on the outside. This next k plus 1 comes straight down, and I'm factoring the 1/2 out of here. I factored out the 1/2, so I have k plus 1/2 factored out gives me 2. 1 divided by 1/2 is 2. And now we have the 1/2 k plus 1 times k plus 1 plus 1, which was our goal. It does take some algebraic manipulation. It really helps to know what your goal is, to know where you're going. So once we've shown this, that it works for k plus 1, we can now assume that it works for all numbers. We'll work through another one before I turn you loose to try your own. Let's prove that 1 plus 4 plus 9 up to n squared is equal to n times n plus 1 times 2n plus 1 divided by 6. The step 1 is always to show that it works for the first term. So our first term is 1. N is 1 times 1 plus 1 times 2 times 1 is 2 plus 1 divided by 6. So this equals 1 times 2 times 3 divided by 6. 1 times 2 times 3 is 6 divided by 6, which is 1. So it works for the first term. Step 2 is our assumption. We're going to assume that it works for n equals k. 1 plus 4 plus 9 up to k squared is equal to k times k plus 1 times 2k plus 1 divided by 6. There's our assumption. And then we're going to prove that it works for the next number. To prove that it's true for the next number, k plus 1, because we had k squared at the end, we're going to add k plus 1 squared to both sides of the equation. And what we'll get on the right-hand side is k times k plus 1 times 2k plus 1 divided by 6 plus k plus 1 squared. Our next step is to write out the goal. Where are we going with this? So in the original sum, we now want to replace our k, every k, with k plus 1. So the goal will be k plus 1 times k plus 1 plus 1 times 2 k plus 1 plus 1 divided by 6. That's what we're aiming for. So let's start off with the sum that we had, which was k times k plus 1, 2k plus 1 divided by 6 plus k plus 1 squared. We added k plus 1 squared to both sides of the equation. First thing we want to do is get a common denominator. So we'll multiply top and bottom by 6. I'll just abbreviate there for space. Then I want to factor out k plus 1 from both of my terms. I have two terms here, one here, and there's my second one there. So I'm going to factor out a k plus 1 from both of those. So on the outside, I'll have k plus 1, and then I'm left with k times 2k plus 1 plus 6 times, this was squared, so I have 1 left. Why did I factor out the k plus 1? Because that's the first term that I'm looking for. And all of this is over 6. You always want to keep an eye on the goal. Where is it we're going? So I accidentally erased all my work there, so I had to rewrite it. We have our goal up here. This was our last step. I'm going to stop writing it over 6 just to save space. Oops, this is all over 6 here. So we have our k plus 1 factored out. Now we need to figure out this from this. So the next thing I'm going to do is multiply all of this out. I'm leaving our k plus 1 on the outside. And then I'll get 2k squared plus k plus 6k plus 6. Remember, that's all over 6. I'll combine my like terms here. 2k squared plus 7k plus 6. Now I'll factor this into two binomials. And I'll have my 2k and k. And I want 6 at the end and 7, so I will do 2 and 3. That will give me 4 plus 3 is 7. And now I'm getting close, because here's my 2k plus 3 and the 2 times k plus 1 plus 1. I'm going to switch the order here, and I'll get my k plus 1. Then I'll use this one, which is k plus 1 plus 1. And then that's the middle term there. And then this one, I'll factor out 2 k plus 1. There's my 2k plus 2 plus 1 more. And all of that is over 6. I could not have done it if I had not written out my goal and knew where I was going. So now that I have proven it, I can tell you that we have proved that it is true for all numbers. Give this one a try. See what you can do. Remember all the steps. Find your goal. Go as far as you can. And now to leave you, just for fun. If Einstein and Pythagoras were both right, then E equals m times a squared plus b squared. See you in class.